Hello, we're going to have a look at Level 3 Calculus 2025 examination, 91577, apply the algebra of complex numbers to solving problems. I already have a video up for questions 1 and question 2, and a supplementary video about one of the questions in question 1, one of the parts of question 1. But we'll move on and we'll start with question 3 today. And question 3 says that they tell us one solution of a quadratic equation, and they say the quadratic equation has real coefficients, and we are to find the quadratic equation in terms of p, giving your answer in the form ax squared plus bx plus c. What we know, or what's important in this question, is that it tells us that the quadratic equation has real coefficients. And that's important because there's a theorem that if a polynomial, and a polynomial is a quadratic is a simple example, it's a polynomial of degree 2, the highest power, but a cubic would be a polynomial, a fourth power expression like this would be a polynomial. If a polynomial has real coefficients, then the solutions are 1, real, or 2, complex conjugate pairs. That is, every solution has to be either a real number or they come in pairs. So that means that when we're told one solution and it's a complex number, we know that there is another solution that is a complex number. So we know x equals 2 minus root pi will be a solution. And we also know, because it's a quadratic, that there are only 2 solutions. Therefore, these are the only 2 solutions. There are multiple ways to get an equation, but if we rewrite these 2 equations in the form x minus 2 excuse me, is equal to root pi, there'll be a plus up here, there'll be a minus down here. If we put them together and make that plus or minus, because then if we square the equation, yeah, oh dear, don't know where the sneezes have come from. We square the equation, we get x minus 2 squared is equal to, squaring plus or minus will always give us a plus, squaring a square root will give us what's under the square root, and squaring I will give us I squared. So this is x squared minus 4x plus 4, expanding that out, is equal to minus p. So x squared minus 4x plus p plus 4 plus p is equal to 0, is in the form that is required. And I suspect you get all of the credit for doing that. There's another way here. If this is a root, then x minus 2 minus root pi is a factor. So we could write out the 2 factors and multiply them out to get a quadratic. You'd get x squared, you'd get x, and I'm going to treat all of this together, you'd get x times that, so that's plus minus 2 plus root pi, and then x times this, so it's going to be another minus 2 and minus root pi x, and then plus, you get this times this. Now this is effectively a difference of squares, so you get the square of the 2, and you get minus pi squared. and that will be, well, the plus pi is going to cancel with the minus root pi here. The minus 2's are going to combine together, so we'll get, I didn't square this, we're going to get x squared minus 4x, and then plus 4, and minus p, I squared's minus 1, so you get plus p. So that's the same quadratic as we've got over here. This is just finding the quadratic expression, function, if you like. So we do need to write it in the form of an equation that they required. And again, I suspect this will get you all of the credit. There's one little thing about the question that I don't like, and that's this word the in here, because there's not actually a solution to this equation. In fact, the general solution that we expect, let's carry on in red, if we've got this root and this root, then all we know about the quadratic, let's call it Q for quadratic, of x, is that it has the form a times x minus 2 minus root pi. And we use that in some questions in this course. And when you multiply this out, you're going to get a times, and you'll get the quadratic that we found. But there's nothing in this question that tells us any information to find a. So we can't find a based on the information in the question. And the question does ask for a specific quadratic equation. So in my view, the question is flawed, because we can't actually find an equation. We can find equations for which this will be a root and it will have real coefficients, but that is an equation, a quadratic equation, not the quadratic equation. Anyway, that's just a minor flaw, but you should be able to do the algebra and get the solutions one way or another. Part B, just expand and simplify, so that's squaring a bracket. You just square the first term, the a is under the square root, you get two lots of a combined term, the I is not under the square root, and you get plus the square of the second term. So squaring square root of 3a becomes 3a. Multiplying it, well, they're multiplying out this bracket. It turns out we can get 3 times 12 is 36. The square root of that's 6. 6 times 2 is 12. So minus 12. We've got a squared. The square root of that is a, and then times I. And then when you square this one, you get 12a, and then I squared, which is negative 1, which will give a negative here. So this is 9a minus 12ai. It says expand and simplify. This is simplified. Arguably, you could take a common factor out and consider this simplified as well. I'm not sure where they will require you to go, but I think this should be fine, but maybe this is better. There is a little bit of a problem here as well. This thing here is, well, let's just look at the root 3a, root 12a. If you write that as minus 36a squared, and then you take the square root of 36 is 6, and if you write this as a, that's not actually quite correct working, because the square root of a squared is actually equal to the absolute value of a, not just a. If a is negative, then you have to take the positive amount, because this is a positive square root. It turns out, if you do all the algebra very, very carefully in here, that you do get from this step to this step, this expression to this expression. But I suspect that the markers aren't looking at the niceties there, and just assuming that you can do all the algebra like this. But as I said, this algebra is technically only true when a is bigger than 0. So really, we need to do some more work, but there's so few lines and so much work to do. So I think this is okay. I just need to quickly revisit part B, because I've got 3a here and minus 12a, that should be minus 9a. And then it's a factor of minus 3 that could be taken out, and you'll get 3 plus 4. So sorry about that, a minor error, but best to get these correct. Thank you very much. Part C, solve the following equation for x. I'm going to just multiply this out. 3 times 1 is 3. 3 times 2 root x is 2 root x. 2 times 3 is 6 root x. And 2 root x times 2 root x is 4x. Again, dealing with these square roots is a little bit tricky, but I might have to look at it again afterwards. The 6x's cancel from both sides, and now we get an equation. It's got 4x here. It's got 2 root x here, plus, and it's got 3 here, minus 5. So that's minus 2 equal to 0. We can divide through everything by 2, and we get a quadratic equation. It doesn't look like a quadratic, but if we take root x as our variable, then this is root x squared. So we can factorize that as 2 root x times root x. Now we want to get plus root x, so we want plus 1 here to give us plus 2, and then minus 1 here to give us minus 1. That's 0, so this says that root x has to be a half, which is x is a quarter, or root x equals minus 1. And root x is always positive, so this is not possible. If you thought that you can just square this and get x equals 1, then if you check that, you'll see that it doesn't work, because our equation becomes 1 plus 2 root 1, 3 plus 2 root 1, which is equal to 1 plus 2 is 3, and 3 plus 2 is 5. That's 15, and that's not equal to 5 plus 6 root 1, which is 11. So this really is not a solution. Now this one here, though, it will check out. So, well, let's put it in. 1 plus 2 root a quarter, 3 plus 2 root a quarter. Square root of a quarter is a half. Half of 2 is 1, so this is 1 plus 1 is 2. And this is 3 plus 1 is 4. That's 8. And 5 plus 6 root a quarter. Don't need the parentheses. This is a half. That's 3. That's 5 plus 3. That's 8. And that checks out here. So this really is a solution, and this really isn't a solution. Part D, one solution of the equation 3z cubed plus pz squared plus qz minus 8 equals 0 is z equals I plus 1 plus I. And notice here, compared to the quadratic equation earlier, I'm going to run out of room, I think, where we had ax squared plus bx plus c equals 0 is the form they wanted. They've given this form and they've put in some of these coefficients. And that allows us to find a particular equation. So we can find particular values for P and Q that will make this equation true. When they don't specify any of these and only specify the roots, there's more than one equation. So there's an inconsistency here between part A and part D, in that this equation has a specific set of roots and a specific form. Part A had specific roots, but there wasn't a specific form. We have to constrain one of these, like make A equal to 1, so that you can find B and C. Anyway, the procedure is pretty much the same, though, or at least the start of it. We've got one root. They always come in complex conjugate pairs, so we know that this is also a root. And that means z minus 1 equal plus or minus I is an equation that's satisfied by the roots. If we square that, we get z squared minus 2z plus 1 equals I squared, which is negative 1. So we get z squared minus 2z plus 2 equals 0. And this will be a factor. So if this is a factor, the other factor has to be linear. So let's just call it a z plus b. And that will give us our cubic that is given in the question. And we can use this information to find out these values here and these values here. So we can find all of these things from this equation. If we look at the coefficient of z cubed, the only way you can get z cubed is to multiply the z squared by az. So az cubed has to equal 3z cubed. And I wrote, I only did one wrong. I wrote x as the variable there. So this means that a has to be 3. And skip over z squared and z. If we just look at the constant term, the only constant term comes from here. Maybe I should do that in a different color. So that means that b times z, that's 2. That's better. 2 times b has to equal negative 8. And that implies that b is negative 4. and together these imply that 3z minus 4 is a factor, therefore z equals 4 over 3 is a root. And the question says find the other two solutions of the equation. So we've got one solution here. The complex conjugate was a second solution, and this here is a third solution. And then we also have to find the values of both p and q. If we go back over here, if we look at the coefficient of z squared, unlike z cubed and the constant where there was only one way, there are two ways to get these. So z squared is going to be z squared times b, and it's going to be minus 2z times a. So that means bz squared minus 2az has to equal pz squared. And since we know a and b, 3 and negative 4, we can work this out. Oh, that should have been the z squared. Az 2z. So b is negative 4. Negative 4 minus 2 times 3 has to equal p. So that means p is negative 10. And if we look at the z coefficient, the way to get a z coefficient is minus 2z times b and 2 times az. So we get minus 2bz plus 2az has to equal qz. So therefore minus 2 times minus 4 plus 2 times 3 has to equals plus 8 plus 6 equals 14. So therefore q equals 14. And we found P and Q. And we found the three roots. We've got two equations in complex numbers. It's a simultaneous equation. So if we call the top equation equation 1, the second equation 2, one way to solve simultaneous equations, these are just linear equations, just a linear factor times u, a linear factor times v in both equations. Just the coefficients can be complex here, so we expect to get complex solutions. If we take equation 1 and multiply by I, then we get u times I squared, that's minus u, plus 2vi equals 3i. And the beauty of that is that if we add this new equation, which we'll call 3 perhaps, then the u's will cancel each other out. We'll eliminate them. So this is the elimination method for solving. So over here we're going to get 2i plus 1 minus I times v is equal to 3i plus 4. Just adding the two equations together, there's no u's. So that means v is equal to 4 plus 3i. And we want to divide by this. So that's 1 plus I. And the standard way when you're dividing by a complex number is to multiply by the complex conjugate in the numerator and the denominator. That gives us 4 ones are 4. I like to do the real parts together, so that's 3 times I squared minus 3, and an I squared is another minus, so it's plus 3. And then the complex parts, 4 times minus 1 is minus 4, and 3 times 1 is plus 3 I. And this bit here becomes 1 plus 1. So we get 7 over 2 plus minus, looks like minus 1 over 2i. So that's V. And then to find U, we've just got to use one of the other equations. I suggest this equation 3 is a good equation to use. From equation 3, we can get U is equal to 2VI minus 3I. VI minus 3I. So that's 2 times 7 over 2 minus a half I minus 3I. The 2 cancels with these two 2's on here, so it's 7I minus I squared, that's just plus 1, minus 3I. So that looks to me like it's 1 plus 4I. And that's our U value. And we're done. So thank you very much. Any questions, put them in the comments. And we'll see you next time.